So now that we've talked about lambda expressions, we've talked about method references, it's time to kind of take a step back and kind of look under the hood and see where are all these things coming from the point of view of the underlying Java type system, or more specifically, the modern Java type system. And so we're going to start by a discussion of something called Java functional interfaces. And we won't get very far in today's lesson, but next time we'll pick up where we left off. And after I give the intro to the concept of functional interfaces here, then over the next few lessons, we'll talk about concrete examples of common Java functional interfaces like predicate function, bifunction, supplier, and consumer. These features, this concept of functional interfaces in conjunction with lambda expressions and method and constructor references are very important. They're important because they're important as the basis of Java functional programming, but they're also very important as the basis for its concurrency and parallelism and asynchrony frameworks. And so that's really why we're focusing on this stuff in a class on parallel functional programming, because if you don't understand the functional part, then the parallel functional part will make no sense because we're going to re-leverage these features elsewhere in the class. So what is a functional interface? A functional interface is an interface that contains only one abstract method. And if you've done a lot of Java programming, you probably have already run across some functional interfaces. Runnable is a functional interface. It has one abstract method. Callable is a functional interface, has one abstract method. So there can be only one, like the famous movie Highlander. We use functional interfaces as the types whenever we have methods whose parameters are going to require or going to allow lambda expressions or method references to be passed as an argument to the method. So here's an example that will hopefully make this more clear. And this is actually from my EX16 folder in my GitHub repository. So this particular example is really cool. I have a bunch of different ways to implement factorial computations. I have a parallel way of doing it and a sequential way of doing it and a couple other approaches as well. And I want to be able to test how long it takes for these different implementations to run. So I wrote a little helper method called run test, and that's going to record and print the time needed to compute the nth factorial. Well, what I do here to keep this nice and abstract is I pass in a parameter called fact for factorial, which is in fact an instance of a function, where a function is an interface that we'll talk about next lesson. But for right now, just think of a function as something that takes a parameter of type t, performs some or applies some kind of computation to it, and returns the result of type t. And so we're going to use this to parameterize the factorial implementation. So this is a great example of behavior parameterization. And the way we use the fact parameters, we say fact.apply. And apply is the abstract method, the single abstract method that's defined in the function interface. So it'll go ahead and do whatever the computation says to apply the function on the parameter n. And you can see this is kind of getting into the weeds, but you can see how I take a snapshot of the current time before we start applying the factorial, apply the factorial, get the result back, and then we compute how long it took, and then we will print the results so you can see which one is fastest. We can pass in different method references in this case to have different implementations of factorial. One of them here is sequential, using sequential streams. One of them is parallel, using parallel streams. And if you run this test on a chipset that's a multi-core chipset, you will see that the parallel version is way faster because it uses parallel processing than the sequential version. So this is just a nice example of behavior parameterization. Just for kicks, here's the implementation of the factorial method for doing parallel computations. I won't get too far into this because we will cover it later, but in a nutshell, what we do is we take n, which is the parameter, which is a big integer, and we go ahead and we compute ourselves a range of long values from 1 to n, and then in parallel, we're going to go ahead and convert each of those longs into a big integer. And then we do what's called a reduction. And those do pairwise, essentially multiplications, starting at the value 1, which is how factorial works, until we've reduced everything in parallel, and we end up with a single result, a single reduced result, which is the nth factorial. And again, we'll talk about this in more detail later, but if you want to play around with the example now, you'll see how it works. It's really cool. So let's kind of summarize the common functional interfaces you're likely to run across. So turns out that there are scores or dozens of functional interfaces that come out of the box with Java. And there's actually a ridiculously large number of them. And some of the interfaces that come out of the box are defined to handle so-called reference types. Those are types that are basically classes in Java. And then there's also a whole pile of similarly named functional interfaces that deal with so-called primitive types. So these would be things like integer, long, double, and so on and so forth. And the reason for this is just because of the way that Java is defined to have two type systems. They have reference types, which are based on classes, and then we have primitive types, which are built in. And the reason we do this, the reason why Java does this, is to avoid the overhead of so-called auto-boxing. So if you use the primitive types, then it won't, if you use the functional interfaces for the primitive types, it won't give you overhead for auto-boxing. This is kind of a weird quirk. It's something that I think, honestly, C++ does a much better job of than Java, but there's historical reasons why it works this way in Java, so we just have to kind of suck it up and deal with it when you're dealing with Java. So one of the consequences of this is there's kind of an explosion of Java functional interfaces, and that can be a little daunting at first when you're first exposed to this. You're like, oh my gosh, where do I start? But it's a really good idea to learn what's in the Java functional interfaces before you're tempted to write your own. You can always rewrite these things if you're so inclined, but the principles of good code reuse dictate you should try to reuse something before you rewrite it. Of course, this is not the way that the principles of doing your programming assignments for this classwork. You're not supposed to go out and take somebody else's solution and use that as your own. So reuse is something that we do when we're building production code to save time and money, but when we're in classes, we do our own work. But the way things work in the real world is once you've built these abstractions, then you leverage them to avoid having to reinvent the wheel and reinvent the wheel in a way that's not going to be square, which is what happens a lot of times when people reinvent the wheel. So it's a good thing to learn about these functional interfaces, and we'll cover, like I said, some of the most common ones in this course. The ones we're going to focus on will be predicate, function, bifunction, supplier, and consumer. And the reason why I focus on those is those are the ones we typically use the most of when we start programming with things like Java streams, Java completable futures, and reactive streams. However, just to be fun and to give you a diverse perspective, your assignment 1B will give you a chance to play around with a few other things that are not those interfaces. So you'll get a chance to kind of learn those on your own, but they're very, very simple and won't throw you for a loop, I assure you. The examples we're going to talk about, starting with the next lesson, which will occur next class, will all be examples of functional interfaces that are stateless. And that is what you should strive for whenever possible with modern Java. Make your lambdas, your method reference be stateless, because it makes it trivial to scale up your programs to work with parallel processing if you keep your interfaces stateless, because then you don't have to worry about the evil of mutable shared state and race conditions and corruption and all the other bad things that occur if you have side effects with the parameters that you're passing as behavior parameterization into the underlying parts of Java that expect to have lambdas and method references. So that's the overview of functional interfaces. As I said, this is just the building blocks. We will cover a lot more things, but you should be at a point now where you should be able to do assignment 1. And obviously, if you have any problems, don't hesitate to come to office hours or post questions on Piazza.